Hello guys, welcome back to my channel. And in the past couple of videos, I was actually solving the different sections of the ISC 2020 board exam maths paper. So I did section A in two parts and section B in two parts. Now it's time to do the last section, section C, in two parts. And don't worry, unlike section B, I actually did prepare rigorously for section C, and I actually attempted this when I sat for this exam. So don't worry, I will be solving all the questions using standard techniques that this exam required. Anyways, so let's get started. Okay, so first off, we start at question number 19, and it has three subparts. All of them are compulsory. So let's do subpart 1, subpart A, which says the selling price of a commodity is fixed at rupees 60 and its cost function is C of x is equal to 35x plus 750. So in sub question 1, they're telling us to determine the profit function, and then in part 2, find the break even points. So like we do with every question, let's first write the data. Let's convert this information from English to math. So the selling price of a commodity is fixed at rupees 60. So the price of one commodity is rupees 60. So call it the demand function. Small p is say rupees 60. And the cost function, let's just write the cost function, 35x plus 750. Okay, so um, we can actually determine the revenue function from this data, because the revenue function is the demand function small p multiplied with the number of items that you are selling. So 60x, that's the revenue function. So for subpart 1, they tell us to determine the profit function. So capital P of x, the profit function, is actually the revenue of x minus the cost of x. So it's like saying how much you produce in sales minus how much it costs you to produce each commodity. So the revenue function is 60x, we just calculated that, minus the cost function. So minus 35x minus 250, and that simplifies to 25x minus 250. Fine. That was part 1. Now part 2 is telling us to find the break even points. So the break even points occur when the profit function is 0, which means that revenue of x minus the cost function of x is equal to 0. And if you just take cost function on that side, we have cost function of x is equal to revenue function of x. Okay, so break even points are those points where you actually you actually get back the cost, the money you lost in production when you're selling all that stuff. So it's the point beyond which you actually start getting something in your pocket, because until the break even point, all you were getting was used to overcome the cost of production. So that will mean profit is equal to 0, right? We have profit function as 25x minus 250 being equal to 0. Solve this simple linear equation, you will obtain x is equal to 10. So when you sell 10 products, that's when you'll overcome the money you lost in production with the money you gained in sales. So moving on to question 19, but subpart B, which says the revenue function is given by r of x is equal to 100x minus x squared minus x cubed. Find part 1 the demand function, and part 2 marginal revenue function. So what we know is revenue function is 100x minus x squared minus x cubed, and we need to find the demand function small p. But if you remember that the revenue function was the demand function small p multiplied with the number of commodities you sell. So the demand function will be revenue divided by x, a revenue function divided by x, and when you do that you'll have 100 minus x squared. And for the marginal revenue function, mr of x is by definition the derivative of the revenue function with respect to x. So we need to differentiate 100x minus x squared minus x cubed with respect to x. So we get 100 minus 2x minus 3x squared. Yeah, that's pretty much it. Okay, so subpart C, for the lines of regression 4x minus 2y is equal to 4 and 2x minus 3y plus 6 is equal to 0, find the mean of x and the mean of y. Okay, so given these lines of regression, let me write them down. 4x minus 2y is equal to 4, 2x minus 3y, taking the 6 on that side, negative 6. We need to find the mean of x, call that x bar, and the mean of y, call that y bar. Now, if these two are the regression lines, then we know by a special property of regression lines that um, if you solve them simultaneously, the solution you will get is actually the mean of x and y respectively. So we need to solve them simultaneously. So what I'm going to do, I'm going to simplify this first equation and divide by 2 actually on both sides. So 2x minus y is equal to 2. And I have 2x minus 3y is equal to negative 6. So subtracting this second from the first, the 2x is cancel out. 3y minus y, 2y is equal to 8. Which means that y is equal to 4. But what did I say? That solution of y will be in a mean of y, right? By the property of regression lines. So mean of y is 4. And if you plug this back into, say, the first equation, you have 2x minus 4 is equal to 2. So 2x will be 6, x is 3, but that's the mean of x, right? The solution. So we know the mean of x and the mean of y by solving these regression um, lines simultaneously. Okay, so officially moving on to question number 20. Now it has two subparts and you can do either. So there's an option between subpart A and subpart B. And naturally, like we did for section A and section B, I will be doing both. So first let's do subpart A. The correlation coefficient between x and y is 0.6. If the variance of x is 225 and the variance of y is 400, mean of x is 10 and mean of y is 20, then find the equations of two regression lines and the expected value of y when x is equal to 2. So let's just write whatever is given to us. So the correlation coefficient, we officially by convention call it r, is 0.6. Variance of x, and we write variance as standard deviation squared of x, is 225. So we can find the standard deviation of x because the standard deviation in this case will be more useful, which turns out to be 15. And we know the variance of y, so standard deviation squared of y is 400. So the standard deviation of y is nothing but 20. Okay, armed with this information now, wait, there's more. Mean of x bar is 10, and y bar, mean of y is 20. Yeah, now we're done. So let's actually do sub part 1. Find the equations of two regression lines. So for that we need the regression coefficient of x on y and y on x. So regression coefficient of y on x is given by the formula r times standard deviation of y over standard deviation of x. So that becomes 0.6 times 20 over 15, which can be simplified to 0.8. Okay, so now using this information, we can find the regression line of y on x. The formula for that is y minus y dash is equal to byx times x minus x dash. So y is the variable, y minus y dash is 20, we know that, mean of y, is equal to, we calculated bxy to be 0.8 times x minus mean of x is 10. So now you can simplify this, 0.8x minus, I believe, 8, and y will therefore be 0.8x plus 12. So that's the regression line of y on x. Fair enough. Okay, that's one. So let's find the other regression line of x on y. So we need coefficient of regression of x on y. The formula for that is r times the reciprocal of this. So standard deviation of x divided by sigma y. So that will be 0.6 times 15 over 20, which turns out to be 0.45. And now we can find the regression line of x on y. Formula for that is x minus mean of x is equal to bxy times y minus mean of y. So that will become x minus 10 is equal to 0.45 times y minus 20, making x the subject of the equation. We have 0.45 plus 1. Okay, that's entirely subpart 1. Now subpart 2, we need to find the expected value of y when x equals 2. So by this we know that y depends on x, right? So y depends on x, so regression line of y on x. So there's this y on something if that variable depends on that. So y on x because y depends on x. So we use this equation, y is equal to 0.8x plus 12, and we plug in x equals 2, yeah. So we get y is equal to 1.6 plus 12, which turns out to be 13.6. And with that we're done with subpart A. Okay, so moving on to question 20, but the optional subpart B. We need to find the regression coefficients byx and bxy and correlation coefficient r for the following data sets. So 0.2, 6, 8, 4, 5, 7, 6 and 5, 2. So what I'm going to do is actually tabulate this raw data, and then we can use the formula to calculate the regression coefficients bxy and byx respectively. So yeah, let's get to it. So what I've done is I've tried my best to draw a table, and that will help us write down points. So call this x, call this y, and let's write all these points. So we have 2, 8, 6, 8, 4, 5, 7, 6 and 5, 2. Then the next column will be for x, y. This will help us in our calculation. So let's calculate that. 8 times 2, 16, 8 times 6, 48, 5 times 4, 20, 7 times 6, 42, 5 times 2, 10, Then we have x squared 4, 36, 4 squared 16, 49, 25. Then we need a y square, so it's 64, 64, 25, 36 and 4. Okay, so what I've done is I've added a row at the end that's sort of like the totaling space. So sum of this entire x column is 24, sum of y 29, sum of xy is 136, 130, 193. So okay, so the thing is, sometimes I'm like really bad with like calculations, so if I make any mistake, please excuse me, because it's the method that matters in this video more than what the final answer turned out to be. Okay, so let me calculate bxy first. So the formula for that is sum of xy minus sum of x times sum of y over a number of terms divided by sum of y squared minus sum of y the whole thing squared over n. And yeah, let me do that down. So sum of xy we know is 136 minus sum of x is 24, sum of y 29 over, there are 5 terms, divided by sum of y squared is 193 from this table minus sum of y the whole thing squared. Sum of y is 29 squared, again divided by 5, and that by my calculations is negative 16 over 124, which you can still reduce to negative 4 over 31. And let's keep it this way. I mean, in the real exam, you would have written some decimal points for this, but let's just keep it this way. Then we have byx, which has a similar formula. So sum of xy minus sum of x, sum of y divided by number of terms. So the numerator is the same, divided by sum of x squared this time minus sum of x the whole thing squared over n. So then that turns out to be negative 8 over 37. I mean, you can plug in, let me plug in if you want. So 136 minus 24 times 29 over 5 over 130 minus 24 square over 5. So as I said, that turned out to be negative 8 over 37. And now keep it as it is. We need to find r, and how do we connect r and these coefficients of regression? R squared is nothing but byx multiplied with bxy. So the negatives will cancel out. We have 8 4s are 32 divided by 37 times 31. Okay, and what we are going to do is going to take the root of that, root of 32 over 37 times 31. So square root is positive or negative, but we are going to choose the negative branch because both my bxy and byx are negative. So r has the same sign as byx and bxy, and one great thing is byx and bxy have to have the same sign. Otherwise, we've made something wrong in our calculations. So forget the positive, we are going to take the negative branch. So that answer turns out to be negative 0 0.167029. And I believe that's the end of the question. Moving on to question 21, which was exactly like question 20 in the sense that it had two subparts of which you could choose either one. So let's do subpart A first, which says the marginal cost of the production of the commodity is 30 plus 2x. It is known that fixed costs are uh, rupees 200. Find 1. The total cost. 2. The cost of increasing output from 100 to 200 units. Okay, so we know the marginal cost MC of x is 30 plus 2x, and the fixed costs are expressed as the cost function evaluated at 0 is 200. Okay, that's our data. So now doing subpart 1, we need to find the total cost. So C of x, we need to find the cost function. So there is a connection between marginal cost and cost. So the marginal cost, and whenever the word marginal is included along with a quantity, just like it was with a marginal revenue, it means a derivative of that quantity. So derivative with respect to x of the cost function is 30 plus 2x. So in order to find our cost function, we need to integrate with respect to x, 30 plus 2x, right? Basically antiderivative or indefinite integral. So when we actually do that, our cost function is 30x plus x squared plus constant of integration, I don't know, call that d. And this is where we use this initial data of c of 0 being equal to 200. So if you say c of 0, all the x terms will go to 0. We just have d, and that we know is 200. So d is 200. And when you plug that into the total cost function, you have x squared plus 30x plus 200, and that's the required total cost in part 1. So now part 2, it says the cost of increasing output from 100 to 200. So that's saying, so cost of 200 minus cost of 100. So if you say start producing 200 products, so how is it, how much more costly is it compared to production, the cost incurred in products producing 10 products? So we just plug in this stuff. So 200 in the cost function. So 200 squared plus 30 times 200 plus 200 minus, now the 100 part, 100 squared minus 30 times 100 plus negative 200. So this cancels out. We have finally 3000 plus 30,000 being equal to rupees 33,000. Yeah, that's actually the increase in cost from, say if you increase from 100 to producing a 200, that's how much more you'll have to pay. So moving on to question 21, optional subpart B, which says the total cost function of a firm is given by C of x is equal to 1/3 x cubed minus 5x squared plus 30x minus 15, where the selling price per unit is given as rupees 16. Find for what value of x will the profit be maximum. So let's first write the data. Selling price per unit is actually referring to the demand function. So small p is 6. And using that we can find the revenue function, because that's demand times x, so 6x. And we know the cost function to be 1/3 x cubed minus 5x squared plus 30x minus 15. And it looks like we need the profit function. That's what we want to maximize. So profit is revenue of x minus, the cost of x. So revenue turned out to be 6x minus 1/3 x cubed minus 5x squared plus 30x minus 15. So all of this actually simplifies to negative x cubed over 3 plus 5x squared minus 24x plus 15. That is actually the profit function. Now, since we need to maximize profit, so we need to maximize the profit function. This actually becomes an optimization problem, right? Optimization problem, because we have functions that we need to optimize or maximize in this case. So to do that, we need to calculate the derivative and set it to 0. So d over dx of p of x, call that p prime of x or the marginal profit. Now, yeah, no need to write that down, is derivative with respect to x of negative x cubed over 3 plus 5x squared minus 24x plus 15, and that will become negative 3 and this 3 will cancel, x squared plus 10x minus 24, and we need to set that to 0, right? Because at the point of maxima or minima, the any function's derivative will be 0. So now throwing the negative, on dividing by negative on both sides, we have x squared minus 10x plus 24 is equal to 0, and this is a normal quadratic equation. So x squared minus 6x minus 4x plus 24 is equal to 0. So x times x minus 6 minus 4 times x minus 6 is equal to 0. Factorize out x minus 6, you have x minus 4 is equal to 0. These are the solutions. So the solutions are x is equal to 4 or x is equal to 6. And which of these is the point of maximum? Well, we don't know, right? So what we're going to do, what you can actually do is, plug in 4 and 6 inside the profit function and check which of these is greater, and then that will be naturally the point of maximum profit. Or what you can do is you can do the second derivative test. The second derivative test, which tests for local maxima and minima. So we need to find p double prime of x, second derivative of p with respect to x. So you differentiate p prime of x. So d over dx of negative x squared plus 10x minus 24. So when I do that, I have negative 2x plus 10. That's p double prime of x. And now let's plug in each of the points. So first p double prime of 4. So when I do that, I have negative 2 times 4 plus 10, which turns out to be 2, which is greater than 0. And the p double prime of 6, if we plug that in, negative 2 times 6 plus 10 is negative 2, which is less than 0. And when the second derivative turns at that point turns out to be less than 0, then that point is your point of maximum. So x is equal to 6 is the point of maximum profit. because at that point your graph will look like this. So at, say, this is x equals 6, you'll have a derivative 0 like we set, and the second derivative is negative because it's a concave down like this. So that's why it's like a peak. But if you look at it, x equals 4, the derivative definitely is 0 because this tangent line is flat, but the graph is concave up, so this is like a valley. So it's like a minima. So x equals 6 it is, and they had told us to what value of x, right? So x equals 6, profit will be maximum. There, we've solved it. Okay, so now moving on to the final question 22, which was for 6 marks. And this is actually a question in linear programming. So there was a lot of graphical data plotting that was required during the exam. So they provided graph papers. But anyways, let's solve it now. It says a company uses 3 machines to manufacture 2 types of shirts, half sleeves and full sleeves. The number of hours required per week on machine M1, M2 and M3 for one shirt of each type is given in the following table. So here's the table. Half sleeves require, say, 1 hour on machine 1, 2 hours on machine 2, and 8/5 hours on machine 3, while full sleeves require 2 hours on machine 1, 1 hour on machine 2, and 8/5 hours on machine 3. Now, they've given us conditions. None of the machines can be in operation for more than 40 hours per week. The profit on each half sleeve shirt is rupees 1, and the profit on each full sleeve shirt is rupees 1.5. How many of each type of shirt should be made per week to maximize the company's profit? So now what we're going to do is look at this table and define our variable. So on the 3 machines, what 2 quantities are common? That's right, number of full sleeve shirts and number of half sleeve shirts, right? So what I'm going to do is I'm going to define, first of all, let number of full sleeve shirts be y, and let number of half sleeve shirts be x. And this is really useful because that allows us to actually write mathematically these constraints that are given. So they're saying that none of the machines can be in operation for more than 40 hours. Okay, so machine 1, the time taken is 1 hour per half sleeve for one half sleeve, and 2 hours for one full sleeve. Say we have x half sleeves and y full sleeves, so the total time will be x times the time required for one half sleeve, or x times 1, plus, because we need the total time for one full sleeve, 2 times the number of full sleeves, y, and that has to be less than or equal to 40, because um, machines, none of the machines can be in operation for more than 40 hours per week. And hours, check for the unit, guys, because sometimes they might just trick you with the units. So this is, say, time constraint for machine 1, and we can actually, if you want, just simplify this. X plus 2y is less than equal to 40. We can do this for machine 2 as well. Similar process. So 2 times x plus 1 time y should be less than and equal to 40. Again, call this time constraint for machine 2. We can do this for the machine 3 as well. 8 over 5x plus 8 over 5y is less than or equal to 40. So time constraint for machine 3. Okay, so we have three inequalities. Call them say 1, 2 and 3. So now what we're going to do is actually convert these inequalities into equalities or equations for lines, and then find the boundary region of find the boundary of the region that we'll be encompassing by this inequality, because a linear inequality of this is actually a region before or after a line which is the boundary. So we need that line which is the boundary, and then we'll define if it's the region before or if it's the region after. So now for 1, convert this into an equality. So we have x plus 2y is equal to 40. Now find two important points. Set x equals to 0 and you'll get 2y is equal to 40 or y is equal to 20. And then the other point where you set y to be 0, you have x as 40. So these are the two important points required for sketching this line later on with the graph. And for our inequality, which was x plus 2y is less than equal to 40, let's do an origin test. So plug in 0, 0. You have 0 is less than 40, which is true, right? So this region, shaded region, will be towards the origin. This stands for towards the origin, because origin satisfied this inequality, right? So it's origin and all the points before this boundary governed by this line will be in the feasible region of this inequality. Okay, so let's do this similar thing for 2. So we have 2x plus y is equal to 40. Now the two important points are 0, 40 and 20, 0. And the inequality that it satisfied was 2x plus y is less than equal to 40. Plug in 0, 0, it will be still be 0 will be still be less than 40. So again, this will cover the region towards the origin. And let's do this for 3. So we have 8 over 5x plus 8 over 5y is equal to 40. Stuff can simplify, so we have x plus y is equal to 25. So the points that we care about are 0, 25 and 25, 0. And the inequality that will satisfy should be x plus y is less than equal to 25. I'm just simplifying this. And if you plug in 0, 0 is less than 25, so it will be the region that's towards the origin that is feasible for this. So what we need to do for our region to satisfy all three inequalities is to find a common feasible region that satisfies all these constraints, and we can best see this on a graph paper. That's why I have these grid lines, so that I'm going to construct a graph of these three lines and we'll see how that works out. Okay, so tada, I've actually drawn the first quadrant here successfully. Call this the x-axis, this the y-axis, and now let's actually label them. Call this the origin. We start at 0, 0, and let's take divisions of 5, because if you look at these points, multiples of 5 would really help. Okay, so what I've actually done is made divisions of 5, and now let's plot these points. So point 1, 0, 20. So that's this point. and 40 comma 0, which is that point, and let's join them. Okay, and let's actually label this line. This line turned out to be x plus 2y is equal to 40. So x plus 2y is equal to 40. That's this line. And since it's towards the origin, let's mark it this way, region that's towards this origin, all this region. Now next line that we have is 0 comma 40, which turns out to be this point, terminal point, and 20 comma 0, which is this. Now let's connect them. Okay, and the equation for that was 2x. Equation was 2x plus y is equal to 40. Okay, and then last point is 0 comma 25, which is this, and 25 comma 0, which is this. So connect them. Okay, and wait, for the previous line it was towards the origin. I forgot to actually mark that. And this new line is x plus y is equal to 25, again towards the origin. So it's all the collective area, so all the area that's before these three lines. So it's this area, the feasible region area. And you can't just go past any one of the lines, because then you'll be actually escaping from one of the possible solution area. Okay, and then now what we do is, after getting the feasible area, look at these boundary intersection points. So call this point A and call this point B, and you can deduce by looking at the graph, or you can solve simultaneously the equations for these two lines. So for point A, it's the intersection of x plus y is equal to 25, and this line x plus 2y is equal to 40. Okay, you have negative 5 is equal to negative 15, which means y is 15, and when you plug it into this first equation, you have x equaling 10. So a now is 10 comma 15, and you can see from the graph 10 comma 15. And now for b, you can solve simultaneously the equations. 2x plus y is equal to 40, intersection of this, and x plus y is equal to 25. Subtract second from first, you will end up with x is equal to 15, and if you plug that into this second equation, that will mean y is 10. So b is 15 comma 10. 15 comma 10. And we forgot to mention what function we have to optimize. So we have to maximize the profit, right? Let's first define the profit function. So the profit of as a function of x and y is given by, well, the data is here. Profit on each sleeve shirt is 1, and how many sleeve shirts are there? Half sleeve shirts are there, x. So 1 times x is x, plus the total profit, that's why plus 1.5 on each full sleeve shirt, and how many full sleeve shirts? Y full sleeve shirts. So 1.5 y. So we need to maximize p of x comma y subject to the above constraints. So all these above constraints, all these stuff, all this stuff that we have, equations 1, 2, and 3. So what I'm going to do is I'm going to check each point, plug it into the profit function. So plugging in A into profit function, you have profit of 10 comma 15. That will be 10 plus 15 times 1.5, which turns out to be rupees 32.5. And when you plug in B, you have profit on a 15 comma 10, which turns out to be 15 plus 10 times 1.5, which is rupees 30 precisely. And which is greater? Well, point A, right? So maximum profit can be attained by not selling, say, making X is half sleeve shirt. So 10 half sleeve shirts and 15 full sleeve shirts per week. You can say maximum profit of rupees 32.5 if you want to be more specific, but that's pretty much the answer. How many subject to the constraints? Well, 10 half sleeves and 15 full sleeves. That's the answer. So hey guys, that's it for today. So we've in this way covered up all three sections of ISC 2020 math board paper. And in the meantime, stay home, keep doing math, stay safe, have a great day, and peace out. I'll be back in Gamma Digamma season 2 with more interesting and exciting content. So stay tuned for that. Peace out.